Hey everyone, this is Bradley Bush with another algebra video for you. If this is your first time to my channel, I'm thrilled that you're here. Welcome. If you're coming back, that's even better. Thank you so much. If you enjoy what you see here, please consider subscribing to the channel or give me a thumbs up or leave a comment. Today, we're talking about summation notation. Summation notation is a concise way to write a really big sum, and I think it's kind of neat. So our first step will be to discuss what is summation notation, and I already just gave you a preview, so that might go fast. Then we'll discuss the notation that's associated with summation because it's kind of different and you might not have seen it, and it looks really terrible, but it's not. And then last, we will have 4 worked examples. Let's start. A quick note before we get into the summation, we've got to talk about a sequence because we need that for our summation. So what is a sequence? A sequence is an ordered collection of objects. So kind of like this. This is the Fibonacci sequence. Repetition is okay, and you just have a collection of items. The terms here, individual terms like 1, 1, 2, 3, 5, those are all elements or terms of the sequence. And you can have an infinite number of them, or you can have a finite number of them. The Fibonacci sequence is a really cool sequence. It appears all over in nature. For example, the number of petals on a daisy, or the number is a Fibonacci number. The number of sunflower seeds in a sunflower head is a Fibonacci number. The number of leaves on a tree is a Fibonacci number. It's kind of crazy how much the Fibonacci sequence appears in nature. But that's a sequence. So summation is when you take the first n terms of a sequence and you add them up. That's not a difficult concept at all, right? You're just adding a bunch of terms. But you've got to understand what a sequence is, which is just a collection of items, and then you add those terms up. That's your sum. But we need a concise way to write it because you could potentially have a very, very large number of them. And it's kind of inconvenient to write a very, very large number. So what we do is we use this little notation. The weird looking E there is a capital sigma. It's a Greek letter. And that just means sum. So you'll sum everything that's in here directly to the right of the capital sigma, the summation sign. So you take that thing, so here we have a sub I, and we're going to add it to itself a certain number of times. We have a lower limit of summation, which is the bottom here, I equals 1. So we start at 1. This I here on the A will change every time we sum. And we're going to add it to itself n times. We'll go from 1 to n. So we're going to sum the value a sub I from 1 to n. That's how you read that. You can see I've written out the answer here to the right. So this summation, this really, really concise writing here is really, it just means I take a sub I and I copy and paste it n times. And then the only thing that changes is the I. So it goes from 1, starts at 1. So what we see right there at the lower limit goes from 1 to n. So 1, 2, 3, all the way up to n. Let's look at an example. Expand and evaluate the sum. Here we are summing negative 2 to the k minus 5 from k equals 4 to k equals 7. How many terms and how many instances or parts in our summation do we have? We start at 4. We'll have 4, k equals 4, k equals 5, k equals 6, and k equals 7. We have 4 terms here. 4 different terms in our sum. Each time we literally just copy and paste the negative 2 to the k minus 5 and plop it in, and then put an addition symbol in between each time. So we're just adding them all up. That's really all we're doing. It's pretty straightforward, right? Once you see what goes on. It looks nasty, but it really is not. And now all I do is I need to take these k's and I need to write them or update them according to what k is. In our first one, k is 4. Let's write 4 here instead of k. The next one, k is 5. In the third one, k is 6. And in the fourth one, k is 7. Now we just do some algebra. Negative 2 to the 4 is 16. Minus 5 gives us 11. Negative 2 to the 5 is negative 32. Minus 5 gives us negative 37. And negative 2 to the 6th power minus 5 is 64. Minus 5, which is 59. And then negative 2 to the 7th power minus 5 is negative 128. Minus 5, which gives us a negative 133. And then we add up 11, negative 37, 59, and 133, and we get negative 100. And that's the value. That's the result of our sum. The sum of negative 2 to the k minus 5 from k equals 4 to 7 is negative 100. It's kind of a fun way to write that. I think it's fun. And if I'm being honest, I think writing a capital sigma is kind of therapeutic. It's kind of like raking one of those small rakes over those little teeny sandy area boxes that, you know those Zen gardens that they have. Okay, that was a little TMI. Next example, expand and evaluate the sum. This sum is I squared plus 1 from I equals 1 to 6. How many times are we going to copy and paste I squared plus 1? Well, we're going to have an instance for every time I equals 1 to 6, and that is just 6 times. Let's write them all out. In fact, we have them here. You see them already. We've written them out right here below. I equals 1, 2, 3, 4, 5, and 6. You can see all of them. There's a plus in between everything because we're summing, right? That's what the summation notation means. And each time we are changing I. So let's change I. Here, I equals 1. The first spot. The second spot, I equals 2. So let's put a 2 in there. The third, I equals 3. The fourth, I equals 4. The fifth, I equals 5. And the sixth, I equals 6. This is actually nice. We start at 1 and go to 6, but we don't have to start at 1 and we don't have to end at some nice number like 6. We could change it up a lot. We could, in the first example, we started at 4. And we can actually count backwards even. We could start at something and count backwards. But here for these examples, we are going to count forward. So 1 squared plus 1 is just 2. 2 squared plus 1 is 5. 3 squared plus 1 is 10. 4 squared plus 1 is 16. 5 squared plus 1 is 26. And 6 squared plus 1 is 37. We add all those together, the 2, 5, the 10, the 17, the 26, and 37, and we get 97 in total. So the sum of I squared plus 1 from I equals 1 to 6 is 97. Let's do another one. Expand and evaluate the sum. We are summing 3 from I equals 1 to 5. Your first reaction could be, where's the I? And it's not there. So what do? Well, we do the same thing we did for the rest of them. We're going to take whatever is to the right of the summation and we're going to copy and paste it a certain number of times and put a plus sign in between all of those copy and pastings and add them up. And if there isn't an I, then we don't change anything. This is kind of like multiplication, if you think about it. 3 is the thing that's to the right of the summation, the capital sigma. So we're going to put 3 down, and we're going to do it how many times? We start at 1 and we go to 5, so that's going to give us 5 times. We have 1, 2, 3, 4, 5, and each time we're just putting the 3 just as it is. And because there's our 5 times, because there's no I, nothing changes. And then we just add up all the 3's. And how many of them are there? There are 1, 2, 3, 4, 5, which gives us 15. That's just like 5 times 15. So you can look at this actually as a multiplication. This right here is multiplication. Kind of interesting. Answer is 15. Let's look at another one. This is our last one. Expand and evaluate the following sum. This sum is -1/2 raised to the i-th power. It's going to be interesting because I will go for positive and negative as it goes from 1 to 4. And we have a negative inside. So every time there's a positive number of times that we multiply something by itself, we'll end up having a positive result. And when there's I think I just totally said that wrong. Just in case I did, every time there is an odd number of times, an odd exponent, the quantity will be negative. Every time there's an even exponent, the quantity will be positive. That is what I meant to say. Let's take our quantity that's to the right of the summation symbol. Here it's -1/2 to the i-th power. And we're going to copy and paste it. It looks like 4 times because we're going from I equals 1 to 4. So we have I equals 1, I equals 2, I equals 3, and I equals 4. I've copy and pasted them below. I put a plus sign in between them, and we're ready to go. I do need to change the I, though. So I here equals 1, I equals 2, I equals 3, and I equals 4. Now all we have left is just to do some algebra. -1/2 to the first power is just -1/2. And -1/2 squared is positive 1/4. So I'm squaring the top and I'm squaring the bottom. And the negative out front also. Sorry, this is the cubed one, but I meant over here. So -1/2 to the third power is -1/8. -1/2 to the fourth power is positive 1/16. I need to add these all together, and I can't do that unless I have a common denominator. So it looks like 16 is going to be my common denominator. I need to then put in a bunch of fractions to get a common denominator. I have a 2 here, and I need it to be a 16. I'm going to multiply by an 8/8. Let's look at the next one. I've got 1/4. It needs to be a 16, so I'm going to multiply by a 4/4. Excuse me. I've got the hiccups. -1/8. It needs to be a 16 in the bottom, so 2/2 and 1/16 works already. We simplify even further, and we have -8/16, 4/16, -2/16, and 1/16. Now we can add them all, the numerators, all together over the same denominator, and we get -5/16. So -1/2 to the I, if we sum that from I equals 1 to 4, gives us a -5/16. Hope this was helpful and you enjoyed it, learned something, and have a great day.